game plan. Last time, which was just yesterday, yesterday evening, which may seem like a long time ago to you. Yesterday we talked about order from disorder. This is the challenge of quantum spin liquids. Normally when we have a large degenerate manifold, what happens is fluctuations, anisotropic and quantum fluctuations, and or fluctuations, select ordered states from within that manifold. But if we're looking for a quantum spin liquid, that's not what we want. So we want something that was dubbed So today's the last part of our series on topics in frustrated magnetism, and today we're going to talk about quantum spin liquids. Last time we talked about order from disorder. The order from disorder, rather counterintuitive notion. Fluctuations, anisotropic thermal and or quantum fluctuations, actually select lattice symmetry breaking ordered states, spin ordered states, from a manifold of classical degenerate states. Okay? This is clearly not what we want if we're interested in a quantum spin liquid. So in some sense, what we want to do is we want to know how can we overcome order from disorder. Indeed, what we want, which is the more intuitive notion, is disorder by disorder. Okay? Now, one of the questions that we're going to look into is what happens if we look at frustration, and most of our discussion so far has been classical or semi-classical. What happens if we include quantum fluctuations? And one way of looking at that is through the transverse field Ising model. Okay? So we'll talk a little bit about that and about very simple Ising spin liquids. Then we'll talk about recent experiments. I mentioned to you yesterday that originally the idea of looking for quantum spin liquids was motivated by the group rates. But most people would say that probably that's not necessarily so relevant for those systems. However, the resurgence of interest in quantum spin liquids is based in experiment. Not so much the group rates, but the point is there are a host of recent experiments which actually suggest that the idea of a quantum spin liquid may actually be realizable. Then, in the last part of the talk, I'd like to tell you about a very exciting development. One of the things that we always enjoy in physics is when we have cross-fertilization from other areas. Okay? And what's happened recently, one of the big challenges in trying to understand a spin liquid is how do you identify something by what it's not? A spin liquid has no broken symmetry, it has short-range correlations in spin and time. How do you actually probe that? Turns out you can take ideas from quantum information theory, the notion of entanglement entropy, and that's actually been applied to some of the systems that were inspired by experiments. So I'd like to tell you about that. And I'll end with summary and open questions. I'm indebted to my friends Leon Balance, Roderick Rösner, and Shivaji Sandhi, both for sharing their ideas with me, but more importantly for this talk, for sharing their slides, as you'll see. Okay, so let's begin. A brief history of magnetism. Remember we talked about how ferromagnetism, the first talk, was discovered, of course, many, many years ago. And it took a long time to get anti-ferromagnetism proved experimentally. And what was the problem? Well, I've alluded to this, but let's be a little bit more specific. Néel believed in an up-down anti-ferromagnetic state. And however, Landau pointed out that this Heisenberg Hamiltonian, which was already known at this stage, that if one looked at this Hamiltonian, that the antiferromagnet was not the quantum ground state. In fact, one had fluctuations around that. In fact, his suggestion was that the quantum ground state was actually singlets. And as we discussed in the first lecture, then enter Anderson and Kubo, and they showed us that even though it may be, Néel's state may not be the true quantum ground state, for many spin configurations, the fluctuations, the quantum fluctuations about this ordered state are sufficiently small that for timescales of interest to us, we might as well think it's order. Okay. But there's been an interest in magnetism in these singlets for a very long time, going back to Landau. Okay. Then in 1987, as we discussed yesterday, Phil Anderson pointing out, well, first of all, in the 70s, Phil Anderson pointing out the dearth of 2D spin-a-half antiferromagnets, said maybe there is an issue about singlets. Okay, then of course came the cuprate superconductivity, and so then the question was, suppose you had a spin liquid and then doped it, could you get novel superconductivity? Okay. And yesterday we talked about this simple spin liquid model that Benoit and I worked on many years ago, and Yoffe and Larkin. Yoffe is now my colleague at Rutgers, actually, and Larkin worked on simultaneously. So in some sense, the first lecture we were talking about this aspect of frustrated magnetism. Last lecture we were talking about this one, and now we're going to ask what could be happening in there. Now, spin wave theory can't really answer that question, okay? Because what we did was basically a Ginsburg kind of argument. We can say what's not there, but we can't say what is there. Okay? So all we can say is something interesting is going on there. Okay. Now, let's get back to the experimental signature of a frustrated system. Remember that at high temperatures, if we look at the inverse susceptibility, at high temperatures we have a spin gas, a paramagnet. Then between the Curie-Weiss temperature and the Néel temperature, we have something that Villon called a cooperative paramagnet, and then we have an antiferromagnet. Okay? So this is a system with local moments, and Art Ramirez suggested a frustration parameter, which is the ratio of the Curie-Weiss theta that comes from, of course, the extrapolation from the high temperature susceptibility over the Néel temperature. And he pointed out that if this ratio is very large, that's his working definition of a frustrated system. Now, in both lectures, people have asked me about specific heat. So let me also say that specific heat is also an interesting way of determining whether or not you have an ordered state. So just let's remind ourselves. Could I please have the screen up a little bit? If it's not too much trouble. Oh, can you see this? Okay. Oh, turn on the light. Sure. Thank you. Okay. So if we have a long-range ordered state, it turns out that CV, it's a specific heat, is of order T to the D. Okay? And this is basically looking at the low-energy hydrodynamics. So I don't need to write that. So let's just remind ourselves as we're waking up where that comes from. A quick derivation is, of course, you know that the average energy goes as the density of states times the energy, I'm not worrying about h bar here, over e to the 8 omega over at minus 1. And we know that n of k goes like k to the d, but now we want to know what n over omega is. Okay? And here we use the dispersion. And this is what we expect if we have a long-range antiferromagnet. We use the dispersion that omega goes like k, and that means that this goes as omega to the d. Okay, so now we have that the density of states, which goes as dn over d omega, looks as omega d minus 1. So then, if we look at this and put that in, we basically get t to the d plus 1 times something that we don't worry about, some constant, and that tells us that CV goes as t to the d. So in other words, in 3D, CV should go as t cubed. The reason I mention this is that a number of experimentalists, pretty much led by Art Ramirez, their smoking gun well, not smoking gun, but what they usually do on a frustrated system is if this frustration parameter is large and the specific heat does not conform, I've lost my pointer, if the specific heat does not conform to this T to the D behavior, then they start suggesting that people do neutron scattering and other things. Okay? All right, so you can see that the dispersion here is going to play a very important role. And for example, what we talked about yesterday, the dispersion will go like k squared in one direction, k in the other direction, so you can see it might affect the specific heat. All right. Oh, thank you. So, what we're interested in then is we're interested in looking at a cooperative paramagnet, and this was called by Villain a classical spin liquid. You may remember that Villain was also one of the earliest researchers to discuss order from disorder. That was partly because of his frustration in trying to find a cooperative paramagnet. He was looking for a system that didn't order classically as he went down in temperature, and he found that his efforts were thwarted always by this fluctuation phenomena. That's how he found order from disorder. So we have, remember that we have a frustration-induced large degeneracy of the ground state manifold, and it's accidental. It's not symmetry related. You can't go from a symmetry operation. It's not like in a ferromagnet, for example, where you go from a symmetry operation of all up to all down. Okay? And what we're looking for is a system with short-range correlations in space and time. Short-range correlations in space, you know what that means. Short-range correlations in time means we don't want any freezing. Okay? Now, the challenge is, of course, order from disorder. And as we discussed yesterday, fluctuations usually select an ordered state. But when might this break down? Okay? Well, we can get, it turns out that we can divide up the entropy in two parts. The discrete entropy and the continuous entropy. When I say continuous entropy, each spin is going to have thermal fluctuations, let's talk about classical, thermal fluctuations about its equilibrium position. Okay? So by definition, this continuous entropy is going to be extensive. It's going to scale like the number of spins. What we need is for the discrete entropy to scale with the number of spins, and in particular, the only way we'll get breakdown of order from disorder is a numbers game if this S of D is greater than S of theta. So I'd like to remind you, this is very similar to an issue in electron propagation. In particular, thank you. In particular, you may be aware that if we take an electron and we are interested in its propagation in its disordered medium, then we have, this isn't so good, we have a bandwidth. So let's talk about the delocalization transition. Delocalization criteria. What we have is W, which is a bandwidth. And this favors delocalization. Can you see in the back? Good. Please let me know if you can. This favors delocalization. And then we might have the square root of a root mean potential. Okay, R max of random potential. And this inhibits diffusion. And the standard delocalization condition is that the bandwidth has to be greater than the root mean squared of the random potential. Well, in our case, it's the configurational entropy. You can think of the system as cruising around in this ground state manifold. The discrete contribution to the entropy is going to favor delocalization, but the continuous part going to favor localization. Okay? The idea is you localize in the state which has the maximal number of continual fluctuations. So in some sense, the way we have the delocalization criteria, here we have the absence of fluctuation selection. Now this usually doesn't happen because, first of all, it's rare to have the discrete entropy extensive. And furthermore, you have to be able to enumerate states. You actually have to count it. So what Benoit and I did many years ago was we took a rather unphysical, but could I have it down again, please? Thank you. Unphysical, but nice for analytic calculations lattice, namely this Hasumi lattice. In particular, the exact enumerations of states are actually possible, is possible, on recursive structures. And we like this Hasumi lattice that you see here, and we were able to actually come up with an example where order from disorder fails. Okay? But as you can see, this is not exactly something you're going to see in the lab. Okay? But the point was, this is a structure where we could actually count these states, and we could actually show that it failed. And what was interesting was it even failed when the states were inequivalent. Okay? But it was a question of ramping up this. Okay. All right, so we were able to find classical spin liquids. But now I remind you that a spin liquid is actually, a liquid is continuously connected to a gas. So you might say, well, classical liquids are continuously connected to gases. They're not a distinct phase of matter. Of course, the way that a liquid might be interesting compared to the gases is in its dynamics, for example, in its glassiness. But maybe classical spin liquids are not the way to go. By contrast, we know that quantum liquids can be distinct states of matter, and we have two very nice cases, of course, the fractional quantum Hall effect, and also superfluid helium, which has a very subtle form of broken symmetry. So we know that quantum liquids can be phases unto themselves and have very interesting properties. So that's what we're going to go for. So let's return for a moment to the counterintuitive order from disorder. Thermally, it tells us that the entropic weight selects a ground state from the degenerate manifold. Quantum mechanically, we find that the zero-point energy also selects from the ground state manifold. Now, a key aspect of quantum mechanics is superposition. And so the question that one can ask is, how do the electrons entangle with one another? So what disorder by disorder is that you take a disordered classical manifold, add quantum fluctuations, and that you get a disordered quantum phase that's a quantum spin liquid. And this is the basic idea behind Anderson and Fasicas. So can we make this work? Well, suppose we're seeking a simple quantum spin liquid. Let's start with a pathological classical spin system. And here we have the Kagame lattice, which we're going to hear about quite a bit today. Because there was a question in the first lecture, I wanted to write this out. The energy of a triangle in the Heisenberg, our nearest neighbor Heisenberg model is, this should be a vector sum. But anyway, the point is that it's a sum of the spins on a triangle plus this constant. That's why I wrote the approximation sign last time. Okay? So you see that here, all the states where the sum of the spins, the vector sum of the spins on a triangle, are ground states. Okay, so we have an extensive number of ground states. Okay, spin wave theory, we have highly perturbative quantum corrections. Spin wave theory, the approach is completely uncontrolled for small s, and so we need new approaches, particularly for spinets a half, where quantum fluctuations are important. Okay, so we need something new. So what we're asking is, if we have degeneracy plus quantum fluctuations, what do we get? Okay, that's the plan. So we can get degeneracy with geometric frustration, But one way of getting quantum fluctuations is to put on a transverse magnetic field. Okay? So this is in some sense the fruit fly of quantum phase transition problems. The idea is let's look at a transverse field Ising model. Here we have an Ising model with a ferromagnetic interaction. Okay? And our spins are in the z direction. We put on a magnetic field in the, a magnetic field in the transverse direction, so it couples to Sx. And what we have is, in this side, here we have T versus gamma. Sorry, this is a G, but I'm using gamma. On this side of the phase diagram, we have up, up, down, down. But of course, if the field gets large enough, our spins are going to go to the right in the direction of the field. But that has to be written in this way in terms of the original basis. Okay? And here we have a quantum critical point. So the question you can ask is, what happens if you do this to a system that has a classical degeneracy? And that was exactly the problem that with Roderick and Shivaji we asked. And in fact, what we thought to do is the following. We said, let's take 4 different lattices, all of which have an extensive entropy at t equals 0. These are all Ising systems. Okay? So the 4 we took were the triangular and the fully frustrated. Let me just draw them. The triangular. Thank you. So we have the triangular, fully frustrated square lattice, one of my favorite lattices, as you know. Then the Kagame, and then the fully frustrated hexagonal lattice. Thank you. All right? So those were the 4 we took. Each of these has an extensive entropy at t equals 0. The top 2 have power law correlations. The bottom 2 have exponential correlations. Okay? So the question is, what happens if you put on a transverse field? Okay? To make a long story short, only the Kagame ended up with a disordered system. And in particular, if you look at this phase diagram, you have, well, let's first look as a function of gamma. What we find is, as a function of gamma, if we look, unfortunately this hasn't come out so well, if we look at the spin-spin correlation function, it's exponential for the classical case. The quantum case is slightly enhanced, and in particular the ratio of the quantum to the classical case decays exponentially. So you have to work really hard. And I remind you that the fully frustrated hexagonal, which also had exponential correlations, that actually showed that did not become a spin liquid. That actually became an ordered state. So the point was that the Kagame, the Ising Kagame in a transverse field, was a disorder to disorder transition. What's also very interesting is that if you apply a field in a longitudinal direction, that's in the direction of the Ising spins, okay, what you find is you get a critical phase. So you get power law correlations. All along here we have exponential correlations. Up here we have power law. So extensive classical entropy is not enough. Okay? And in particular, just to give you an idea, even in this simple fruit fly problem, we couldn't just check with one approach. We had to do variational, Landau-Ginzburg, height model, dimer mappings, quantum Monte Carlo, and exact diagonalization. And this is for a system that is not really physically realizable. Okay? So back to quantum spin liquids. Of course, that was an Ising problem. We're really interested in the Heisenberg problem. Okay? But that was sort of a warm-up. So quantum spin liquids, we want a quantum spin system where, once again, there's no spin ordering and no spin freezing. It has no broken symmetry in space or in time. Okay? We expect it to have unconventional excitation, not spin 1 magnons. You remember that in spin ice, we had some fractional excitations. Okay? We know in d equals 1 we have interesting excitations. Now we're expecting that our quantum spin system will have unconventional excitations. And in some sense, one of the reasons people are looking for this so much is you can think of it as an economy strongly correlated phase. All right. As you see, it's a strong coupling. It has less degrees of freedom than doped systems, and the question is, can we get some ideas for how to understand and develop techniques and methods to understand strongly correlated systems with charge? All right. So, one of the exciting aspects that's developed in the last couple of years has been that people have brought ideas from quantum information theory to bear on this problem. In particular, one of the issues that crops up is, how do you say that you have a state that's only defined by what it is not? Okay? So, what's been suggested in the community is to call a spin liquid a ground state of a spin system with long-range entanglement. What does this mean? It means a state that can't be regarded or even approximated as a product state over any finite blocks. Okay? So remember that this is Anderson's RVB state, and in particular, what we have is we have a long-range entangled wave function, which is a complicated thing. And it's hard to work directly with all these coefficients, and a spin liquid can be defined in many, many ways. So one of the approaches that is used a lot in the community right now is a free fermion approach. A useful construction uses a Fermi gas where we have a product in momentum space rather than in real space. So here we have a product, and we construct a spin liquid state with only one fermion per site. Remember, in a spin liquid, what's crucial, and we saw this in the spin ice problem, are the local constraints. When you have a local constraint, then in order to satisfy that constraint, just like we know in electromagnetism, a local constraint often leads to a gauge field. Okay? So many of these spin liquids are studied using the low energy physics, as we saw in a simple case with spin ice, by an emergent gauge theory, with a fermion as a spin. So let me just give you a quick idea of some of the quantum spin zoology. Quantum spins are characterized by the weight of the valence bond partition in the wave function. Okay? They come in many, many varieties, and that's why I said that quantum spin here is zoology. They come as gapped and gapless. Their excitations obey fermion, Bose, and anyon statistics, maybe others, but those are the only ones I know of. And there are two garden variety, common ones that we hear about a lot, basically. One is a U1 state. It consists of unspared spin-ons. It's gapless in 2D. It has strong gauge fluctuations, and it's stable only at t equals 0 and d equals 3. Okay? Another is a Z2 spin liquid. Here, spin-ons are paired. We're gapped in 2 dimensions. We have weak gauge fluctuations, and there's an Ising transition. Now, why is it called Z2? It's called Z2 because its properties are described by an emergent Z2 gauge field. Okay? In some sense, an Ising version of electrodynamics. We have an electric field that's 0 or 1. In other words, we have a magnetic flux. Remember when we talked about spin ice? We had a flux for each tetrahedra. Here we have a magnetic flux that's either 0 or pi. So what happens is that the field is 1 or 0 on a bond, depending on whether the spins at the ends are if we have spins at the ends of the singlets. Oh, if the spins at the ends are singlets or not. Okay? And the point is that electric charges in this gauge field are unpaired spins. So remember, we're writing this as a sum over valence bond configurations. So that's what a Z2 spin liquid is. All right. Any questions? Okay, let's march on. So, 10 years ago, not too many, spin liquids. Leon is from California, so he took a nice picture of the desert. Okay? 10 years ago, there was nothing. Okay? Well, there was a nice desert, but no experimental candidates for spin liquid behavior.
Tony, do you mean of the last two types you had on your list?
No, just in general. Okay?
But don't you get, if you just melt any magnetic system, won't it have both, won't it have no short range
Well,
magnetic photonic properties?
at low temperatures it usually orders. It either orders or freezes.
But in all the cases that we see where you use pressure...
Okay, I'm talking about an ambient pressure right now. Okay, we're talking about ambient pressure, right? And it would be interesting to know more about the characteristics of spin systems at finite pressure. We'll see there's one that's a finite field. Okay? And I haven't seen actually much done theoretically at finite pressure, and that's a very interesting idea. All right. So where do we look? But of course, when I say we, I mean the community. We look at materials with spin half spins, S equals half spins, because that maximizes quantum fluctuations. We look at systems that are frustrated. We might also look at systems that have significant charge fluctuations. Insulators, but where there's significant charge fluctuations. Not insulators, for example. Another approach is to look for exotic interactions, which I haven't talked about so much, but spin-orbit coupling. Okay? So those are some of them. What's amazing is now we have several systems. Okay? You may note that all of them have lattices that we've discussed here. Okay? Now, since we talked so much about pyrochlore the first lecture, let me start by saying that this is a pyrochlore system. We're not going to talk about it very much because it involves a lot of spin orbit, which we haven't really gone through that much. But this is a system that, at finite fields, so this is similar to what Stephen was saying at finite pressure, finite fields, it's believed to have a quantum spin liquid state. What they see is that there are no spin waves at low fields, but at high fields, spin waves emerge, and there's a suggestion that it could be a quantum spin liquid. Okay? Here it's going to be, this doesn't have spin half, but the point is you have, like in the spin ice, you have pseudospins, and in fact you do have spin half in your pseudospins. Okay, so that's just to let you know about that one. Now, this material that I'd like to tell you about a little bit is something that is called Herbert Smithite. I'm sorry, I don't know the background behind this very creative name, but certainly it's a lot easier than saying this chemical formula. This is a spin half Kagame system with a antiferromagnetic exchange that's about 200 Kelvin. Okay? It has no conventional magnetic order down to 50 millikelvin. Okay? So this definitely fills this tells us it's a highly frustrated system following the Ramirez criteria. Okay? And in fact, this is a paper that came out in 2009, which discusses the fact that in neutron scattering, they don't see spin. They don't see any magnetic ordering. As you might guess, neutron scattering is really the way of choice. But once again, we're talking about what's not there. Okay, so these experiments prompted, as always, a synergy between, an interplay between experiment and theory. So people, after seeing these experiments, said, what can we say as theorists about this system? And this is where the synergy between computer information and condensed matter theory came along. The idea was, how do we develop, and when I say we, of course, I mean as a community, diagnostics for states of matter with no known order parameter. So, what people have done is they've done density matrix renormalization group. Now, I'm certainly not an expert on this, but what they basically do is the following. In exact diagonalization, you get the wave function of the system, and you get the coefficients of the wave function in terms of whatever basis set you choose. Okay, so you get weights. And then you could work with that wave function. Now, exact diagonalization is enormously expensive to do it. You can't really go to very large lattice sizes. It's very costly. As I understand it, and I don't, this is just my impressionistic understanding, we know that some of those weights are more important than others. Okay? So what they do in density matrix renormalization group is they only select those weights that are important and then work with them, and then they're able to go to much larger system sizes. Now, this approach and the trick of choosing the weights is something where the approach that's been taken has been specific to one team. Recently, Steve White, who was one of the developers of this technique, has extended it to 2 dimensions, but not for real 2 dimensions, for cylinders. Okay? And this was one of the, applying it, this approach to the Kagame was one of the first times that it was applied. So what they found in this paper on the spin-a-half Kagame is they found that the ground system, the ground state is gapped, and there's no sign of magnetic or valence bond ordering. Okay? So that's what they found. Okay, but once again, what they're saying is what it's not. So this is enter information, quantum information theory. In quantum information theory, people, and this has been used particularly in the area of quantum computation, people look at entanglement entropy, okay? And people look at entanglement entropy to tell us how strongly entangled a subregion A is with the rest of the system, okay? So, and it turns out that we can use what's called topological entangled entropy as a new diagnostics for phases with no known order parameter. Now, for reasons I'm not quite sure about, because I'm new at this, as I've mentioned to you, I'm learning about this with you. This only works for gapped quantum spin liquids. Okay, so let's take that as a given. Only works for gapped quantum spin liquids. So what they do is the following. They look at the entropy S of A, and that tells us the measure of how strongly entangled the subregion A is with the rest of the system. Okay? It turns out that if they have a smooth boundary, as you would have for a cylinder, then S of A is a function of L, which should be LA, goes like some coefficient of LA minus some term gamma. Now this gamma is what's called the topological entanglement entropy. It turns out that this gamma is, this gamma is not zero, is finite for topologically ordered states, for example, like the fractional quantum Hall state, but it's zero for states that are not topologically ordered, like the integer quantum Hall effect, band insulators, topological insulators, etc. So this is a way, this entanglement entropy, and in particular this topological entanglement entropy, is actually a way of determining what kind of spin liquid you have, if it's gapped. All right, so then we have these 2 papers that came out last year, at the end of last year, and they used 2 kinds of entanglement entropy, one of Neumann entropy and one of Ranyang entropy. From what I understand, they both came up with the same results, but I'm going to tell you a little bit about this one only because I don't really understand Ranyang entropy. So what these people found is they found that this gamma that we just discussed is very close to log 2. Now, that prompted a lot of excitement and got them an article in Nature. Why is it? Well, let's go back and see what's expected for a Z2 spin liquid. In a Z2 spin liquid, remember in a gauge theory, we have a Gaussian constraint. The usual Gaussian constraint, namely, this. Okay? That's our Gaussian constraint. However, in an Ising gauge theory, thank you. In an gauge theory, our constraint, our local constraint, is going to be this mod 2. Okay? This is our constraint. All right. So, the point is, remember that entanglement entropy is the lack of knowledge about removing a region. Okay? Now, this is our constraint. So, very holistically, as I understand it, the fact that we have mod 2 means we have more information, since any field has to obey this constraint. Therefore, the entanglement entropy should be reduced by this amount, and therefore we expect gamma to be log 2. All right, so there was a lot of excitement and people saying, wow, we finally found a Kagame spin, a Z2 spin liquid. But there's a rub. Can I have this down, please? Thank you. Sorry to go up and down so much. Recently, there were some beautiful experiments by the Johns Hopkins group on this Kagame spin system. This is a group that played a very important role in identifying spin-ons in one-dimensional systems. Okay? What they see is a continuum of spin-on excitations, and therefore they suggest that one has fractional excitations. That's very exciting. What they do not see, they don't see a spin gap. Okay? You might argue that some of the theorists have said there might be disorder. Of course, the experimentalists say that can't be the case. The point is that with all this beautiful numerics and theory and all of that, there's still a lot to do. Okay? So clearly, something interesting is going on, but we don't know yet.
Sorry,
So this is inelastic neutron scattering, and the point is that they see different kinds of spectra than you would expect for spin waves, and this looks very much like what they saw for 1D systems where we know there are spin-ons. Okay. So the point is that the interplay between theory and experiment in frustrated magnetism is definitely alive and well, and there are lots of questions to look at. Okay, so let me wrap up then. Summary for my third lecture. We have breakdown of order from disorder, which we can call the more intuitive disorder by disorder. Surprisingly enough, the intuitive is actually quite hard to get. As you saw, we had to work quite hard to find a lattice that even gave us an Ising spin liquid. So I told you about transverse field Ising models, where we have a minimalist quantum spin liquid. I hope I've given you a flavor for the quantum zoo. There are lots and lots of theories, but I chose to tell you about some that had some experimental possible realization. By definition, most of these strongly coupled theories are terribly uncontrolled, so that's why it's great to have numerics and experiment to sort of keep us all honest. Experiment is wonderful in all this. I think the introduction of ideas from quantum information and quantum computation into this area is very exciting, but as you see, our work is far from done. So I hope I've convinced you that we have lots of opportunities for interaction between analytic, experiment, and computational approaches in quantum spin liquids. We have designer frustrated cold atoms coming soon, and also many fascinating new materials. So there's lots to be done in the future. So let me give you some references for further reading, which helped me in preparing all of this. This is a very nice book on the transverse field Ising model. Interesting enough, this model was originally proposed, to my knowledge, by Dijen in trying to understand quantum ferroelectrics. Okay? So anyway, this is a model that is a very nice way of getting some of the key features of quantum phase transition. I've listed these references chronologically. Frederick Müller has written a nice article on quantum spin liquids, which talks a lot about what was going on at that time. Subir Sachev has a nice article in Science looking at quantum criticality. My friends and collaborators, Roderick and Shivaji, have written an article on Ising models of quantum frustration, which goes beyond what I described to you today. Leon Balance has a very nice article in 2010 as an overview on spin liquids in frustrated magnets. He's also written a more recent article talking about using entanglement entropy as a way of identifying topological order. Finally, a book that has just come out in February this year, I found very useful in particularly learning about materials. And this is a book edited by Mendels, Lacroix, and Mila. And there's some really nice, broad articles about materials theory and, more importantly, experiment. Okay. So, what have we done? Okay. I've tried to give you a sort of topless approach to frustrated magnetism and to give you some flavor of some of the current research that's going on now in the context of some of the work that's happened before. So in the first lecture, we reviewed frustrated magnetism, and then we talked about spin ice, a very seemingly simple system that actually led to some of the ideas that we've seen over and over again, namely the fact that one has a constraint, and therefore the low energy physics of these systems can be explained by divergent gauge theory. Okay? We also learned a little bit about monopoles and talked about about neutron scattering that actually shows that the constraint seems to be obeyed. Then yesterday we talked about order from disorder, and I tried to give you an idea of how this works in some simple models. And one of the unexpected twists of all of this was that there was a link to Ricci flow. Okay? That was something that came out completely unexpected from studying a really simple model. Then today we talked about quantum spin liquids, disorder by disorder, transverse field Ising model, and in particular we talked about how the confluence of quantum information theory and condensed matter theory has led to some really interesting diagnostics for how to identify a quantum spin liquid. However, the interplay with experiment suggests that's not all over yet, and I think this is a very, it's an exciting area. So finally, thank you very much, and best of luck with all your research projects. Thank you.
Okay. Questions?
I think everyone's tired. You might want some coffee. Sure.
So what would you say is the key experiment? It's inelastic neutron scattering?
Yes, yes. So the inelastic neutron scattering shows, first, there's no spin gap, and second, it gives us a feeling that there's a spin-on continuum, and that the excitations are definitely not magnon-like. What they suggest in their paper is that they have fractional excitations, but I think more has to be done on that. But I guess from a theoretical standpoint, all of this very nice computer work that I suggested, it looks like it has beautiful agreement, blah, blah, blah. But the point is, it all assumes a spin gap, and that's not seen experimentally. So right now, we have to try and we as a community have to reconcile that. But I think that this inelastic neutron scattering experiment is crucial.
You mentioned that in quantum spin liquid that might be gapped or gapless.
Yes.
So, and is that only like pair on pair spin-ons? That's only one factor that would determine whether some gapped or gapped or gapless.
Those are only two specific varieties of spin liquids. There are many other spin liquids too. I mean, if you have spin-ons as your excitations, then which are usually spin half objects, then the point is that if you pair them or unpair them, it's gapped or gapless. But you could have other kinds of excitations also.
How to understand like the spin-ons, like like with
Well,
gas?
that emerges from one of these gauge theories. So there are all kinds of crazy gauge theories floating around. So I chose to talk about the one that possibly has interaction with experiment and also where there are merits. Did Stephen have a question?
Yeah, so you had a very long list of different types of thin liquid. Before you actually do the experiment, are there any more general guidelines from theory to know which thin liquid you'll get if you use some tuning parameters to mount a magnetic state?
Okay, these thin liquids appear in situations. So, for example, as always, in strong theories, it depends what approach you use, and you use thin liquid. So there's a lot of uncontrolled behavior here. But for example, on the cadmium lattice, there are a number of gauge theory approaches that suggest that you should get a gapped thin liquid. Okay? And that's what neutron study, which obviously disagrees with that. I think one of the nice things about this area of frustrated magnetism is there's constant interplay. I've shown you in the experiment.
I have a very general question. As you're talking about frustration, also talk about spin gas.
Hard magnet. Spin gas.
Oh, no.
Oh, spin glass. Sorry. I haven't talked about that's a completely different area. I'm happy to make some. A spin glass often have a random, so you often. A cutting edge research area is can you actually get long range time in space without disorder? That's a very interesting. If you have infinite rate reactions, you actually have so the system can get stuck. The system can get stuck. Model, to my knowledge, glass without. However, spin ice that we looked at, I did tell you is at very low temperatures. It's a classical spin liquid that at very low temperature actually increases. And so this. Okay.
Is this work about sure. Just some comment. There's some very recent work about how I said about self-generating glasses that you disorder some sort of kind of branches.
These are field approaches, of course. Yeah.
Does this hold or is it stable towards previous order?
The nature of the meaning is you should be field theory so that the state you want. And we all do that. Okay. So to be honest with you, it's work is very nice. But if you were find it decrease. That's my point. One reason we're frustration is disillusion with states is superconducting. Turns out a superconducting basically thought of as an XY order parameter, and there you can frustrate this with an you can have disorder constant, but we are not with a superconducting with glasses. In some sense, my good parents who had a strong academic where there was class without disorder, and we could understand that. So I Well, first of all, it's very difficult to but the idea that very persist. Just to see how we're doing. These are I'm not sure what it means to have intelligence. You mean that you take a student that is open? I don't really know the methodology. What
just seen any metallic system where you can and if you do that might order this time what magnetic station and it's possible to any of those which fits on this is
Bye.